Hi, good morning. Thank you very much for joining this keynote session. My name is Chris MI. I will deliver a talk today on wireless charging for application in electric ship, trains, electric vehicles, and others. So let me start sharing of my PowerPoint. So thank you again for listening. So today my talk is about the application of wireless power transfer in electric aircraft, railway ships, and road vehicles. Let me start by talking who I am and where I came from. So I came from San Diego State University, which is located in San Diego, California, around 50 miles from the city. As you can see, you get on Highway 8, you will reach the campus within about 15 minutes from airport. Our campus was built in the 1900s, and it's been more than 120 years old, the university. And this is located in San Diego, a beautiful city, and I welcome you to visit. Let me get into the technical content here. So I want to ask everybody a question. Where are we in wireless power transfer? We know that Nikola Tesla developed his very first WPT system in the 1900s, and that is over 120 years ago. And then around 1960, people started to get microwave power transfer. Now remember, this is slightly different than the microwave that you use at home, because that microwave device transfers electricity into heat. But the wireless power transfer we talk about is to transfer electricity to the user end. In this case, it was trying to power a helicopter. Solar-powered satellite microwave power transfer system was developed in the 1970s. Apparently, the power was fairly low at that time. And in the 90s, as we know, the EV1, which was produced by GM, that had this conductive and inductive charger for the electric vehicle. Now that is a contactless charging system, which is different from what we are talking about wireless charging, but still that is a significant advancement in terms of contactless charging, which improves reliability and safety of EV charging. In the late 2000s, we already started to see high efficiency EV chargers. And the low power chargers for phones, laptops, and so on become available in the early 2010s. And it's very popular these days with all kinds of consumer electronics. In 2015, our group developed this double-sided LCC topology that has become mainstream for many years for EV charging circuit design. The high power EV chargers, including dynamic charging, real charging, ships, and even other applications start to evolve around 2015 until today. So with that being said, it looks like technology development seems to be done already. And this is driven by material like lead wire, magnetics, lower power devices, especially looking at this newer silicon carbide device and gallium nitride devices, and also modeling tools that are available for us today to easily develop the transmitting and receiving systems in a wireless power transfer. So with that already being so much technological progress made, what are the challenges today? Well, it seems that it's more like application oriented. So it means that we have the technology, but it's just not prime time for high power wireless chargers to be deployed at this point. One of the key, or many of the key items that are listed here, including size. This is in particular true for high power applications. Foreign object detection has become a very sensitive topic in the past couple of years because the metal material or animals, small animals that get into the transmitting get on top of the transmitting device, it's going to create trouble, like hazardous conditions, even for fire, explosion. That is possible because if you catch fire, if you ignite plastic, metal, which means if there's a metal that can catch high heat and that ignite leaf, plastic, and other things, and then eventually it may propagate to the battery inside the vehicle, which can really cause a harmful condition. Small animals can be killed due to excessive heat. So that is important because if you don't overcome that hurdle, the high power wireless charging is not going to be commercially available on a larger scale anytime soon. The next item is cost. Because when we add in transmitting paths, receiving paths, we are adding additional costs compared to conductive charging. Where the consumer, a consumer is willing to pay additional money to buy wireless charger if they can spend $2,000 less in comparison to buying a conductive charger. Efficiency is still something we're still working on, which means there's loss in the paths, there's loss in the magnetics, there's loss in the laser wire that do not exist in conductive charging systems. Next is standardization and interoperability, because you want different OEMs to make cars that can use the same transmitting path. This, if we make it standard for all the transmitting paths, it's going to hinder the technology advancement, because you cannot design new stuff that is only applicable to one application, not another. And then you have to deal with EMC and human safety issues. Finally, is consumer acceptance. Whether they're going to accept it, whether it's appearance, whether efficiency, cost, the size, all kinds of things, convenience, and so on. So do the advantages override the constraints or the disadvantage of such a system? So finally, I think it's going to be application-specific technology that is going to fly. That's going to fly because that's where it makes sense economically, technically, and for many other reasons that you can imagine. So with that, I want to just dive into, first of all, wireless chargers for cars, buses. They are here today. So I bought two pictures, one from electricity. Dr. Morris presented this at our workshop on wireless power transfer, and another one from momentum dynamics. And you can see whether it's stationary charging, whether it's dynamic charging, whether it's medium power in the kilowatts range or high power in the hundreds of kilowatt range. They're available, but all of the systems still have challenges, whether you talk about the old ones that I mentioned from my previous slide. So how do you overcome them to make these systems commercially available? And you can make this widespread. And then the next application, we talk about electric ships. In fact, this company called Vasila, they developed this wireless inductive charger system for electric ship at 2.5 megawatts. As you can see from the picture, the charging system was on a robotic arm, and the receiving end is on a ship. The good thing, of course, you can charge once the ship reaches the dock. You don't have to wait until the ship is docked to start the charging. But this is apparently have a lot of advantage. For example, safety. You don't have to worry about water erosion, salty water, things like that. But as you can see from this picture, the big mechanical arm and the receiving transmitting pad, those are going to add additional cost to the system. Whether it's feasible, economically viable, that's going to be something we have to wait and see in the next couple of years. In Korea, South Korea, they have developed this megawatt system. The publication claims that 1 megawatt. I heard that they have also developed up to 6.6 megawatt system to charge train or high-speed train. Now, when the train reaches hundreds of kilometers of speed, does it make sense how fast the transition between one coil to another? Because as far as I know, this is still inductive charging. Is it going to work at that kind of speed? So this is something we have to look at. And also the cost. Is it going to be much more expensive than the simple brush type overhead transmission line. Apparently, this is something we have to study. Maybe I can think some of the applications could be only maybe in the tunnel, for example. It's hard to have an overhead line due to the size of the tunnel. And that you may be able to develop a system to just specific to that area of application, or maybe in a parking yard for trains. Well, it's not easy to have this overhead transmission lines in place. So they did testing, as you can see, and it works. A third application I can imagine is this low-speed rail system, where they try to use this maglev system to reduce the noise of the brushes and so on in the residential area. So therefore, you can do this wireless charging to provide power to the low speed, which is more feasible than the high-speed train. Another application will be to use this to transfer for power only for example, for electrical buses, because you can reduce onboard energy storage system, which means you can reduce significantly the cost and maintenance in the long run and the life of the battery. So therefore, this is significant savings if you can do quasi-dynamic charging. When the bus stops, you charge them for 20 seconds, 30 seconds, good for 1 or 2 miles, and then you charge again in the next stop. So this makes sense because you can save battery cost, you can save maintenance cost, you can save manpower because you don't need anybody to pull the cable to charge them anymore. So this apparently makes a lot of sense. The next application will be related to automatic guided vehicles, where you have this small and big. Small ones in the factory with guided yellow tape, with this robotic carts, which can be as small as just a couple of kilograms, as big as a couple 100 kilograms. They carry tools, materials around in a factory. And as big as 50 tons in like a shipyard, where these vehicles carry goods from one point to another, and then load and unload from the ship and load them into a truck. And these vehicles can be very energy consuming because these are huge vehicles that are running at a very low speed. Transfer them to electric vehicles makes sense. However, this vehicle running 24/7. So if you have to charge these vehicles during certain times, it's going to increase the downtime. So having a wireless charging will reduce the downtime because you don't have to pull them out to charge the vehicles. And plus, you don't have to replace those vehicles due to the battery that are discharged. So which means these vehicles are running on a specific track. So there's no worry about foreign objects. There's no worry about alignment, and you can have very high efficiency. So this makes a lot of sense. Another application I can imagine is underwater vehicles. These underwater vehicles, they take a lot of time to drop them onto the seafloor. They have to come back to charge them. They have to seal the ports because at underwater, there's a lot of pressure, and that can cause problem for the charging ports. With wireless charging, well, you can drop this charging pad onto the seafloor. These vehicles can work there, and they can go back to docking station to get charged. The issue is seawater that are conductive, maybe partially conductive, and you basically cannot use capacitive charging because there's no way you can transfer power from one place to another due to seawater, and that basically is everywhere. Inductive charging is possible. Even ultrasonic charging is also maybe feasible. In a couple of years ago, we did this study to develop this multi-stage wireless power transfer system like a domino. The application for this is to power the gate driver circuit in a solid state transformer or in a large switch gear where you have hundreds of IGBTs that are connected in parallel and series. And each gate driver is at a different potential. So you cannot ground them all together. So grounding is a huge issue in this system for the gate drivers, and power supply becomes a problem. You have to have isolated power supply for each gate driver. So in this study, we do this domino type of wireless charging pads, where you transfer power from one circuit to another. So one transmitter to another receiver, it becomes a transmitter for the next one. So we have found that this was very effective, and we were able to achieve like 86% of efficiency at 6 centimeters of distance, up to 200 watts in total. So this is sufficient to drive like tanky drivers. Of course, you have to design many of this to power the whole system. On the other hand, if you look at the low power charging, for example, cell phones, tablets, and so on, I think the key right now is how to design the system so that they can be versatile, position-free, low cost. So some of this study was based on capacitive charging instead of inductive, and it works on a surface like a desk, like a cubicle, for example, where you can put this charging system either capacitive or inductive, where you have these phones can be put either horizontal or flat, depending on the design. In this case, the phone can be either vertical or horizontal. You can still charge the phone even you are holding the phone and you're working on the phone will still be charged. So some of these ideas are still being developed, where you look at the alignment, efficiency, and other things. Primarily, I think the cost is another concern. For EV charging, we're getting bigger. Earlier, I mentioned my electric shift charging at 2.5 megawatts, train charging at 1.5 megawatts. In our laboratory, we also did a preliminary study on a 200 kilowatt fast wireless charging system for cars, where you can see that with this design, we're able to achieve the DC efficiency up to 98%. And we're focusing on still 85 kilohertz, which may not be optimal frequency, by the way. But apparently, the voltage, the higher the voltage, the better the efficiency you can achieve in this system design. So this is one of the study. I want to also dive into some of the studies carried out by other scientists. And then this, I have reference listed here on the slide. Well, this is a study looking at how you can replace the brushes and slip rings with a wireless power transfer system, because the slip ring and the brushes tend to be the weak point for many applications, such as the doubly fed induction machine for wind power generations, right? You have this high power wind power generation system, the slip ring and the brushes tend to be, the weak point have to be maintained in a certain time interval. So if you replace them with a wireless charging system, whether it's inductive or capacitive, that tend to be very attractive application. Another application is with these elevators. And you imagine that you're hopping into an elevator, and the elevator moves, and you get lights inside, you get communications inside, you get buttons, you get even air conditioning inside the elevator car. So have you thought about where is the energy coming from? Well, apparently in traditional applications, they come from a cable. And that cable, because the car is moving, so the cable has to be long enough to accommodate the moving of the elevator. And think about it, that cable will eventually generate resistance, losses, and it's gonna break at some point. So that is the weak point in the elevator system, especially for high-rise, tens of stories of buildings. If you replace the cable, remove the cable, replace it with a transmitter and a receiver on the car, you basically can, or we basically can have a wireless transfer system. Of course, you also need some sort of energy storage on the car when there's no power transfer available. We can possibly build a whole track, like a capacitive, or we can build at each stop on the floor. When the car is stopped, you transfer power in the system. So this will work. And I think eventually this system will save cost, operating cost, maintenance cost, and even maybe even initial cost. The cable is not cheap, especially for long high-rise building. Those cables can be hundreds of feet long, and it costs a lot of money. So I listed a number of applications. I think this is my final thoughts are that the WPT is an enabling technology for many applications. The technology itself is still evolving. IPT and CPT, they're unique, and they can be good for different applications. You cannot rule out one for another. It's going to be application specific. Other technologies, microwave, laser, ultrasound, and so on, they're being studied, and they are good for certain applications. For example, if you have metal enclosure, you have a device inside you need to power up. How do you do it? Well, right now, you cannot transfer that using either capacitive or inductive. Maybe ultrasound is the only solution. Having long distance with hundreds of meters, there's no way you can use near field power transfer, probably microwave, unless it's going to be the solution. So those are going to be developed and studied and be available in the next 5, 10, 20 years. Safety is a major concern for high power systems. When you have this metal, animal, human safety, that has to be studied. The technology has to be developed. I don't think it's this mature technology today to resolve the issue with metal. And just think about it. If there's a metal you detect it, what do? You stop charging. And we tell the owner saying there's a metal. But if the owner is far away from there, can he come back to clean it? Okay? So that one, I pose that question for you, and how we resolve that issue so that the driver comes back at night, they still have power to drive the vehicle. So a Tesla-free world is not likely to happen as Tesla has imagined 100 years ago. It's not going to happen, or at least it's not going to happen anytime soon. So with that, I think the compromise among cost, safety, efficiency, and other factors are going to be key to commercialization of WPT technology. So with that, I want to give you an overview of what we have done recently at the 2021 Wireless Power Week, which composed of WPTC, Wireless Power Transfer Technology Conference, sponsored by Microwave Society, and the workshop on wireless power transfer, WOW, sponsored by PELS. I was the general chair with the coach of Jason Lin and technical coaches from both societies. And the conference was also co-sponsored technically by APS. We had 9 sponsors, exhibitors or industrial sponsors, 3 platinum and 2 gold. And for silver sponsors, I want to thank them for their sponsorship. That make it the conference very successful. And I'll give you a history of the WPW that involved from about almost 8 years ago, like 2013 up to 2018. At 2018, these 2 conferences come together to do a co-location. And next year, this year is in San Diego. Next year, we hope to have a combined conference in France in 2023. This is important. Remember that. We're going to come back to San Diego in person because this year we did a workshop. So we had 9 keynote speakers, 85 papers, 2,500 attendees from more than 20 countries. And we have 9 keynote speakers from low power to high power, from microwave to inductive to capacitive, from theory to application, from history to modern technology. So all these recordings are available on YouTube, and I'll give you the link to where to get it. The WPT school had more than 10 speakers. It was very well attended, probably the most attended tutorial in any conference. We had more than 5,000 views altogether with the WPT workshop. I want also to publicize the PELS Technical Committee, TC9, Wireless Power Transfer System. This is a new TC focused on wireless power. We are recruiting volunteers to work, and we're also working closely with MTT on their wireless power transfer. As I mentioned earlier, the conference recordings of WPW 2021 is still available. You can access either from HOA, the conference platform, or you can go to YouTube /wireless power transfer. You can watch all the recordings of the keynote, technical sessions, WPT school, and the sponsor video. And some additional videos actually also available at their website. 2022 in France. Remember that date, June 4 to 9. So you can submit a paper and you register for the conference. And in 2023, come back to San Diego. We're going to have a huge wireless power conference and expo. And we are welcoming volunteers, authors, and sponsors and exhibits. We are expecting to have 25 exhibits at the 2023 conference. And finally, I just want to do some advertising of our work, our books in this area, and acknowledgement to sponsors as well as students who work in this area. With that, I want to finish the presentation, and I would be happy to answer any questions you might have if there's an opportunity. Thank you very much, and we'll look forward to seeing you in next year and the following year in San Diego. Bye-bye.